held the key to unlocking some of the deepest mysteries of quantum matter and maybe even the future of computing.
It sounds almost too grand, doesn't it?
It really does. Today, we're embarking on a journey through a truly profound concept that connects all these dots. Resonating valence bonds, or RVB.
Right, RVB.
We've pulled together quite a stack of sources for you. Everything from Linus Pauling's foundational 20th century chemistry papers, right up to the most cutting-edge physics research from today.
And our mission, really, is to distill that, to extract the most important nuggets of knowledge and insight, making something that sounds incredibly complex feel, well, accessible and maybe even surprising for you.
Exactly. It's quite the intellectual adventure we're planning. You'll see how RVB started with Linus Pauling's incredible chemical intuition, fundamentally explaining the structure of molecules like benzene.
And then how Philip Anderson, decades later, took that kind of radical idea and hypothesized it, could explain something as monumental as high-temperature superconductivity,
Wow.
leading to a whole new state of matter, these things called quantum spin liquids.
Okay.
And finally, how this surprisingly versatile concept is now pointing us directly towards, well, the very future of quantum computing.
Okay, let's unpack this, starting right at the genesis of resonance. So back in 1916, G.N. Lewis had this really intuitive idea, right? Covalent bonds as shared electron pairs, Lewis structures.
Yeah, the ones we all learn.
Yeah.
Very visual, very useful, but fundamentally classical thinking.
Right, classical. So what changed in 1927 when Heitler and London came along? That seems like a key moment.
Oh, absolutely groundbreaking. They were the first to successfully calculate the bonding properties of the simplest molecule, hydrogen H2.
Just a two.
Just H2, but using the brand new framework of quantum mechanics from first principle. They showed that when atomic orbitals overlap, there's this unique quantum mechanical effect, the exchange interaction, that provides the energy to form the bond.
So not just sharing, but something deeper.
Exactly. It wasn't just a detail. It was really the birth of valence bond, or VB theory.
So if Heitler and London cracked H2, why wasn't that the end of the story? Why couldn't this foundational valence bond theory just scale up to explain everything, say, methane, CH4, with its perfect tetrahedral shape, and 4 identical bonds?
Yeah, you'd think it would be straightforward, but that's precisely where the simple VB theory hit its first major wall.
No.
The basic Heitler-London model just couldn't account for these more complex molecular geometries. Methane's a perfect example. 4 identical bonds, 109.5 degrees apart. How do you get that shape from carbon's native s and p orbitals, which are oriented very differently?
Right, they point along axes, don't they?
Exactly. This is where Linus Pauling made his landmark contribution in the early 1930s, introducing the concept of orbital hybridization.
Hybridization. Okay, break that down for us. What is it in simple terms?
Well, Pauling proposed that an atom's native orbitals, like carbon's 2s and 2p orbitals, could mathematically mix or hybridize to form new equivalent directional orbitals.
Like blending ingredients.
Kind of. For methane, you mix 1s and 3p orbitals to get 4 identical sp3 hybrid orbitals. And guess what? They point perfectly to the corners of a tetrahedron.
Matching the geometry.
Precisely. It was revolutionary because it gave chemists a simple, visual, intuitive way to explain molecular shapes, connecting quantum principles to the actual 3D structure you could measure. The real nugget here is understanding why molecules have the shapes they do.
So hybridization sorted out the shapes. But did this mean valence bond theory was now complete, or were there still, lingering puzzles?
Still puzzles. Even with hybridization, VB theory struggled with certain molecules, specifically those with what we call conjugated systems. Think alternating single and double bonds.
Okay.
A single Lewis structure, even using hybrid orbitals, just couldn't capture their full reality. Their properties didn't quite fit.
So another roadblock.
Yep. And this is where Pauling gave us his second great conceptual leap. The theory of resonance.
Resonance. We hear that word a lot with benzene. So what's the real aha moment here about this idea of superposition?
Pauling said, look, if you can draw multiple valid Lewis structures for a molecule structures that only differ in where the electrons are, not the atoms, then the molecule's true state isn't any single one of them.
Okay, not just one picture.
And critically, it's not flipping back and forth between them like some classical oscillation. No, it's a quantum mechanical superposition of all those structures simultaneously. He called it a resonance hybrid.
A hybrid state.
And the profound insight, the real game changer, is that this quantum superposition fundamentally stabilizes the molecule. It lowers its energy.
Ah, right, leading to what's called resonance energy. So this isn't just a theoretical drawing exercise. It means the molecule is genuinely more stable because its electrons are, spread out, delocalized.
Exactly. Delocalized over multiple atoms, not stuck between just two. And the classic example, the poster child for resonance, is benzene, C6H6.
Which was a huge mystery for ages.
Took decades. Since 1825, Kekulé proposed the famous ring with alternating single and double bonds. But his model had problems. It predicted two different versions of 1-Villary-2 disubstituted benzene, but chemists only ever found one. Plus, experiments showed all 6 carbon bonds in benzene are identical in length, somewhere between a typical single and double bond. Kekulé later suggested rapid oscillation, but that was still thinking classically.
So how did Pauling's resonance fix this? He worked with Wieland on this, didn't he?
Yes, Pauling and Wieland in 1933, they applied resonance theory. Benzene, they said, is a static resonance hybrid. It's mainly a superposition of the two Kekulé structures.
The two main ways of drawing the double bonds.
Right, plus a smaller contribution from some less stable structures called Dewar structures. This quantum averaging, this superposition, delocalizes the pi electrons over the entire ring.
Spreading them out evenly.
Exactly. That's why all the CC bonds end up identical, with a bond order of about 1.5 perfectly matching experiments. And their calculations showed a big chunk of resonance energy, explaining why benzene is unusually stable and reacts differently than simple double-bonded molecules.
A massive success for the theory, then. Solved a long-standing puzzle.
Absolutely. It was profound validation. Now, interestingly, for many years, doing these VB calculations was computationally really hard, much harder than a competing approach called molecular orbital theory.
Right. MO theory kind of took over for a while.
It did, largely for computational reasons. But now, with modern methods, things like natural bond orbital and neutral resonance theory chemists can rigorously reevaluate Pauling's original concepts.
And what's the verdict?
It's stunning, really.
Right.
These modern calculations show that Pauling's qualitative ideas, his intuition about hybridization and resonance, are robustly reflected in the quantitative results. His physical insight was spot on, decades ahead of the tools to fully prove it computationally.
That's amazing. A testament to the power of a good idea.
It really is. And it's precisely that enduring power that allowed this concept, decades later, to undergo this radical rebirth in a completely different field, pushing beyond chemistry into the physics of, strongly correlated systems.
Okay, so a whole new chapter for RVB. Now, you mentioned band theory works well for most metals, but fails for these strongly correlated systems. Why? What's so different about them?
The key difference is that electron interactions are just too strong to ignore or average out, which is what band theory essentially does.
They really knows each other.
Oh, strongly. The dominant interaction is often this powerful on-site Coulomb repulsion, usually called U. Basically, electrons strongly repel each other if they try to occupy the same atomic orbital. It costs a lot of energy.
Okay.
So when this repulsion U is much larger than the electron's kinetic energy, their ability to hop between atoms, you don't get a normal metal. Instead, you get what's called a Mott insulator.
A Mott insulator,
Yeah.
not predicted by standard band theory.
No. Band theory often incorrectly predicts them to be metals. Nickel oxide and EO is a classic example. It should be a metal by band theory rules, but it's a very good insulator because of these strong correlations. The Hubbard model, developed in the 60s, is sort of the minimal model capturing this fight between hopping T and repulsion.
Right, the standard rules break down. And this is where Philip W. Anderson comes in 1973, with a radical alternative.
Exactly. Anderson was looking at the Heisenberg model, which describes localized spins in these Mott insulators. He was particularly interested in cases with geometric frustration.
Frustration, like the spins can't all get what they want.
Precisely. Imagine spins on a triangular lattice trying to be anti-ferromagnetic. Each wants to point opposite to its neighbors. On a triangle, it's impossible for all 3 spins to satisfy that condition simultaneously. Someone's always frustrated.
I see. 2 can't anti-align, but the third doesn't know what to do.
Right. Anderson argued this frustration enhances quantum fluctuations. It prevents the spins from just freezing into a simple, ordered magnetic pattern like a checkerboard Neal state you see in simpler antiferromagnets. It sort of melts the magnetic order.
Melts it.
Yeah.
even at zero temperature.
Mm.
That sounds weird. What does a liquid of spins mean?
It is weird. It means it's dynamic, fluctuating with no static magnetic pattern. And this is where Anderson brilliantly generalized Pauling's chemical idea. He proposed a resonating valence bond, RVB state, as a novel ground state for these frustrated magnets.
Okay, RVB again, but for spins now.
Yes, an RBB state here is a macroscopic quantum superposition of all possible ways to pair up spins on the lattice into valence bonds, where each bond is a spin singlet pair.
A singlet spins pointing oppositely paired up.
Exactly, the magnetic equivalent of Pauling's electron pair bond. Now, any single pattern of these bonds would be a valence bond solid and would break the lattice symmetry. But the RVB state is a superposition of all possible pairings, a dynamic liquid that restores the symmetry, and, crucially, has no magnetic order. This was the first concrete picture of what we now call a quantum spin liquid.
A quantum spin liquid. That phrase itself is something. Okay, so this is a fundamentally new state of matter Anderson proposed. How does this radical idea connect to that huge discovery in 1986, high-temperature superconductivity in the cuprates?
And that discovery just electrified physics.
Yeah.
These copper oxide materials became superconducting at temperatures far higher than anyone thought possible, completely challenging the standard BCS theory of superconductivity.
BCS theory that worked so well for conventional superconductors, right? Based on electrons pairing via lattice vibrations, phonons.
Exactly. But BCS seemed totally wrong for the cuprates. First, their parent compounds, the undoped materials, are Mott insulators, not the metals BCS starts from.
Big difference.
Huge. Second, the transition temperatures, to see, were just incredibly high, seemed way too high for phonon coupling. And experiments started showing that phonons probably weren't the main glue holding the electron pairs together anyway. The old rules just didn't fit.
So the stage was set for a new idea, and Anderson stepped in.
He did, with characteristic boldness. In 1987, he made this audacious hypothesis. What if the undoped parent cuprate isn't just a simple antiferromagnet, but is actually an RVB quantum spin liquid, a pre-existing sea of these resonating, charge-neutral spin singlet pairs?
Pairs already there, before it even superconducts.
That was the radical part. In his view, superconductivity emerges directly when you dope this exotic insulator, when you add charge carriers, usually holes. These holes become mobile, and they allow the preformed singlet pairs to move coherently through the lattice, carrying supercurrent.
So completely different from BCS, where pairs form at the transition temperature.
Totally different. In RVB, the pairs are already there, lurking in the magnetic background. Doping just sets them free to move coherently.
Okay, if it's not phonons holding the pairs together, what is the glue in the RVB picture? What makes these singlets form so strongly?
The glue is the very strong antiferromagnetic interaction between the copper spins mediated by the oxygen atoms in between. It's called superexchange, usually denoted by J. This interaction is what favors forming those spin singlet pairs in the first place in the Mott insulator. And crucially, this J is a very large energy scale in the cuprates, maybe 1,000, 1,500 Kelvin?
Much higher than typical phonon energies.
Way higher.
Yeah.
So RVB theory naturally explains the high energy scale associated with high TC superconductivity and why the transition temperatures are so high. It places the problem firmly in the strong coupling regime, dominated by electron interactions, not weak phonon coupling. The minimal model often used here is the TJ model, which includes hopping and the strong superexchange J, while forbidding doubly occupied sites because of the large U.
This really does sound like a completely different universe from BCS. Could you maybe summarize the key differences for us, just to keep it clear?
Absolutely. It's worth laying them out side by side. Parent state. BCS starts from a normal metal, a Fermi liquid. RVB starts from a Mott insulator,
Okay.
pairing glue. BCS uses the electron-phonon interaction. RVB uses strong antiferromagnetic superexchange, J,
Got it.
coupling strength. BCS is fundamentally weak coupling. RVB is strong coupling.
Right.
Nature of pairs. In BCS, Cooper pairs form at TC. In RVB, spin singlet pairs are essentially preformed above TC in the spin liquid state.
Preformed pairs, key difference.
Superconducting symmetry. BCS typically predicts simple isotropic swave pairing. RVB naturally predicts anisotropic D-wave pairing.
Which is what's actually seen in cuprates, right?
Overwhelmingly confirmed experimentally, yes. That was a major success for RVB.
Okay.
Elementary excitations. BCS has Bogoliubov quasi-particles. RVB predicts these bizarre fractionalized excitation spinions and holons. We need to talk more about those.
Definitely. And final.
Domain. BCS is the theory for conventional low-temperature superconductors. RVB was proposed specifically for these unconventional high-temperature ones.
That's a fantastic breakdown, thanks. Okay, let's dive deeper into that really mind-bending physics, these quantum spin liquids. What exactly is this state of matter? How is it different from just a disordered magnet like a paramagnet?
Good question. A paramagnet is disordered because of thermal energy. If you cool it down enough, it will usually order magnetically or freeze. A quantum spin liquid, or QSL, is fundamentally different. It remains magnetically disordered even at absolute zero temperature.
Zero thermal fluctuations, but still no order.
Exactly. Normally, as you cool a material, its spins will pick a direction, order themselves, and break some symmetry. A QSL refuses to do that. It stays in this dynamic, fluctuating, liquid-like state of spins right down to T0.
So what defines it then, if not order?
Its defining characteristic isn't local order, but rather a global pattern of long-range quantum entanglement. Every spin is intricately, non-locally entangled with many other spins across the entire system. This complex web of entanglement prevents any simple static magnetic pattern from forming.
Entanglement is the key. So how does such a state even form? You mentioned frustration earlier.
Frustration is often the key ingredient, yes. It arises when you have competing interactions that can't all be satisfied simultaneously. The classic case is geometric frustration, like those antiferromagnetic spins on a triangular or Kugome lattice we talked about.
Right, they can't all anti-align.
Precisely. This enhances the quantum fluctuations, effectively melting any potential magnetic order and stabilizing this liquid-like QSL state. But it's not just geometric frustration, there's also kinetic frustration.
Kinetic, related to movement.
Yes. This can happen in doped Mott insulators. Imagine adding a hole. As it tries to move, its motion can be severely hindered by the background spins due to destructive quantum interference effects. This suppression of kinetic energy can itself stabilize an RVB spin liquid, even on lattices that aren't geometrically frustrated.
So multiple routes to this exotic state. Now, I've heard QSLs described as having topological order. That sounds pretty profound. What does it mean?
It is profound. Topological order is a completely new way for matter to organize itself, fundamentally different from the usual symmetry-breaking orders described by Landau theory, like magnetism or crystallization.
Okay, beyond symmetry breaking,
Yeah.
what are its hallmarks?
It has really distinct non-local signatures. One is topological ground state degeneracy. The number of distinct ground states depends on the topology of the surface the system lives on, like whether it's a sphere or a torus, a donut shape, not on its size or local details.
The shape of the whole system matters.
Weird.
It is. Another key signature is the existence of fractionalized excitations. The basic disturbances in the system carry fractions of the electron's quantum numbers, like spin or charge. And underlying it all is that long-range entanglement pattern. The true nugget here is that it's a whole new classification of quantum phases. And you mentioned a connection to high-energy physics, emerging gauge fields.
Yeah, it's quite remarkable. The low-energy physics describing the fluctuations within these topological states often looks like the gauge theories that particle physicists use to describe fundamental forces like electromagnetism. Things like Z2 or U1 gauge fields can emerge dynamically from the interacting spins.
Wow, condensed matter mimicking particle physics. So given how weird they are, how do scientists actually look for these QSLs in real materials? Must be tricky.
Incredibly challenging. Because their defining feature is the lack of conventional magnetic order, you can't just use standard magnetic probes in the usual way.
So what do you look for?
The primary signature is seeing a material with strong magnetic interactions. The spins should want to order, but then finding absolutely no magnetic ordering develops, even when you cool it down to the lowest possible temperatures, milli-Kelvin ranges.
Absence of evidence as evidence.
In a way, yes. Leading candidate materials include Herbert smithite. It's a naturally occurring mineral where copper ions form these beautiful, highly frustrating 2D Kagome lattices. It shows no magnetic order way down low.
Kagome, that's like interwoven triangles, right? Very
Yeah.
frustrating.
Exactly. Also, certain quasi-2D organic materials where molecules sit on a triangular lattice are strong candidates. Experimental probes like measuring specific heat at low temperatures or using inelastic neutron scattering can look for indirect signs of the fractionalized excitations predicted for QSLs.
Okay, let's get back to those fractionalized excitations. This is where it gets really wild. The idea that the electron itself can effectively come apart. Spin-charge separation.
Yes, this is one of the most counterintuitive predictions of RVB and related theories for strongly correlated systems. The electron, our familiar particle with charge E and spin 12, can essentially disintegrate within the
They're like
material.
disintegrate. Seriously.
Well, effectively, yes. Its fundamental properties, its spin and its charge, become decoupled and are carried by entirely new, independent, emergent quasi-particles. This is fractionalization.
So what are these new fractionated particles called?
They're typically called spinions and holons. The spinion carries the electron's spin 12, but has zero electric charge. You can kind of picture it as an unpaired spin wandering through that sea of singlet pairs.
A spin without a charge. Okay.
And the holon, sometimes called a chargon, does the opposite. It carries the electron's charge, effectively plus E, like a hole, but has zero spin. It's like a mobile vacancy in the electron sea.
A charge without a spin. So the electron we normally think of as like a bound state of these two.
Exactly. But in an RVB state, particularly in lower dimensions, these spinion and holon constituents can become deconfined. They can separate and move around independently. This leads to a truly bizarre metallic state, utterly unlike a conventional metal where charge and spin always travel together with the electron.
Mind-bending. Has anyone actually seen this? Is there experimental proof for fractionalization? It sounds almost like science fiction.
It does, but remarkably, yes, there is strong evidence, especially from one-dimensional systems.
One dimension, like chains of atoms.
Exactly. Techniques like angle-resolved photoemission spectroscopy, ARPs, have been used on quasi-1D cuprate materials like strontium superoxide, SrCO2.
And what did ARP show?
It was spectacular. In a normal metal, ARP sees a single peak corresponding to removing an electron. In these 1D materials, that single peak clearly splits into two distinct features in the energy momentum map. These two features correspond precisely to the separate creation of a spinion and a holon. You're literally seeing the electron fall apart in the data.
Wow. Direct observation. What about in 2D, like the high T2 cuprates themselves?
In 2D, the situation is more complex and the evidence is more indirect. Deconfinement is harder in higher dimensions. However, many of the truly anomalous properties of the normal state of the cuprates, the state above T-SOI, are often interpreted as signs of partial or precursor spin charge separation. Things like the resistivity changing linearly with temperature instead of quadratically like in normal metals, and the existence of the mysterious pseudo-gap phase. Many physicists believe these are fingerprints of the underlying RVB physics and fractionalization. Even if the spinions and holons aren't fully independent like in 1D, it's seen as a direct legacy of the RVB paradigm.
Okay, so zooming out now. When you look at RVB's journey, its biggest success seems to be this incredible unifying power. It connects basic chemical bonding with these really exotic quantum phenomena.
Absolutely. In chemistry, it gave the first truly satisfactory explanation for things like aromaticity, the stability of benzene, solved that century-old puzzle.
And in physics for high TC.
There, its impact was immense. It correctly identified the parent state as a Mott insulator, not a simple metal. It naturally accounted for the high transition temperatures because of that strong superexchange glue, J. It accurately predicted the D-wave pairing symmetry, which was a huge win.
And it provided a framework for all those weird normal state properties, right? The pseudo-gap, linear resistivity.
Exactly. It offered a coherent picture connecting all these disparate, strange observations back to the underlying strong correlations and the RVB concept.
But it's not without its challenges, is it? What are the main hurdles the theory still faces?
No theory is perfect, and RVB faces real challenges. On the theoretical side, as we mentioned, it was computationally tough in chemistry for a long time. In physics, despite huge efforts, there's still no rigorous, universally accepted mathematical proof, starting from the basic Hubbard or TJ model that definitively shows it leads to a superconducting ground state in 2D. People believe it, sophisticated calculations support it, but a formal proof is lacking.
And experimentally.
Experimentally, the biggest hurdle is the elusiveness of finding a real material that is unambiguously a pure RVB quantum spin liquid ground state. Candidate materials often have complications, maybe some residual disorder, or competing interactions that muddy the waters.
Hard to find a clean example.
Very hard. And crucially, you have to remember that many of the phenomena RVB helps explain, like D-wave pairing or aspects of the pseudo-gap, are also addressed, sometimes differently, by other competing theories.
So it's not the only game in town.
Definitely not.
Hmm?
Making experimental distinctions between these theories is extraordinarily difficult. There's no single smoking gun experiment yet that says, yes, it's definitively RVB and nothing else. That's why a full consensus on the exact pairing mechanism in cuprates is still remarkably lacking after all these years.
So, a work in progress. But clearly, RVB isn't a static idea stuck in the past. Where is it heading now? What are the new frontiers?
Oh, it's constantly evolving, which is the sign of a healthy scientific idea. Researchers are actively exploring variations and extensions. For instance, triplet RVB, looking at states based on spin triplet pairs, not just singlets, which might be relevant for unconventional superconductivity in other materials, like some iron-based superconductors.
Triple pairs.
There's even wilder stuff like phononic RVB. The idea here is that the resonance might happen between patterns of atomic vibrations, phonons, potentially leading to fractionalization in the lattice sector itself, really out there.
Wow. Resonance of vibrations.
And of course, the search continues for better QSL candidate materials, exploring new compounds with frustrated geometries like kagome or pyrochlore lattices. Plus, there's growing interest in RVB ideas in novel 2D materials like graphene, silicene, germanium. Could they potentially host RVB physics? Maybe even room temperature superconductivity? That's a huge motivator.
Okay, so it's branching out into new materials, new ideas, but the journey doesn't stop there. You mentioned a connection to quantum computing. How does this concept from chemistry and condensed matter physics link to cutting-edge computation?
This is probably one of the most exciting current directions. That long-range quantum entanglement, the defining feature of quantum spin liquids, makes them prime candidates for building topological quantum computers.
Topological quantum computing. How does that work?
The idea is to encode quantum information, the qubits, non-locally within the global topological properties of the QSL state. Because the information isn't stored in any single localized particle, it's inherently protected from local noise and errors, things like stray magnetic fields or vibrations, which are the bane of current quantum computers, causing decoherence.
So the QSL structure itself protects the quantum information.
Exactly. It offers intrinsic fault tolerance. The fractionalized excitations in these states, often called ennions, have exotic braiding statistics how they behave when you move them around each other. Manipulating these ennions in a controlled way could be used to perform quantum computations. So, finding and understanding RVB states and QSLs might literally provide the physical hardware for robust, large-scale quantum computers.
That's incredible. So the quest for understanding RVB is now directly tied to potentially revolutionary future technologies.
Absolutely. It makes the fundamental physics research incredibly relevant.
So when we look back, even if RVB isn't ultimately crowned the final, complete theory for high TC superconductivity, its legacy seems much, much broader, doesn't it?
Immensely broader. You're right. Perhaps the true triumph of RVB isn't whether it perfectly explains one specific material class, but its incredible intellectual trajectory.
How so?
Think about it. It started as an intuitive chemical concept for molecules like benzene. It was reborn decades later as a radical unifying theory in condensed matter physics. And in that process, it forced physicists to develop entirely new fundamental concepts. Quantum spin liquids, topological order, fractionalization, emergent gauge fields.
Concepts that are now mainstream.
Absolutely central to modern condensed matter physics, far beyond just superconductivity. And at the same time, as we noted, it's seeing a renaissance back in chemistry thanks to computational advances, making valence bond theory a powerful tool again.
So it's not just one narrow theory.
No, it's become an enduring paradigm, a powerful way of thinking about the localized, entangled, and correlated nature of quantum particles. And it continues to inspire new questions and discoveries across chemistry, physics, and now even quantum information science. Its influence is just remarkable.
Think about it. From the simple yet perplexing structure of a common chemical like benzene, we've been led down this incredible rabbit hole into a universe where electrons can seem to disintegrate, where reality itself can be topologically ordered at a fundamental level, and where the very fabric of quantum entanglement might be woven into the computers of the future.
It really shows the power of connecting ideas.
It's just a powerful reminder, isn't it, that sometimes the most profound insights come from connecting seemingly disparate fields and just daring to look at the familiar in an entirely new way.